Hello everyone, I'm Boaz, as you all know, and the title of my inquiry 1 is Ready, Set, Ignition. Now, I say this is the title of my inquiry 1. It is also the theme of it, because I actually had 4 experiments by the end. Yeah, 4. It is absolutely ridiculous. So, my journey, so to speak. Alright. Now, a few weeks ago, we all came in, we talked to Ms. Smith, Mr. Allman, and our fellow classmates, and we gave a rough outline of what our experiment was going to be. As some of you may recall, I was going to use lasers and try to set objects on fire, such as a paper towel. Before I actually went out and did this experiment, I tested it. And even with a lens to magnify it, I was unable to catch a piece of paper on fire. So I had to go back to the drawing board. Now, the drawing board brought out another experiment where I tested voltage and if it could set 0.1 grams of fine steel wool on fire. If so, how long would that take? And I'm going to have a video here next. Okay, what we have here is 19.5 volts. This is what it looks like. Yeah, okay, I'm sure this is a fire hazard. And let's try it. It is hot. Hopefully I'm not going to catch myself on fire. Whoa, lots of smoke. Like a whole lot of smoke. Whoa. Actually, it happened. It looks like all of it. A few times. Sparks actually came back and hit me. Yeah. I'll admit that. That was a little scary. Alright. As you remember, I said I had to conduct my experiment 4 times. First one was a laser. 2 and 3 was experiments like this. Now, 2 and 3. They did not work because, as you see this pie pan here, it's aluminum. Therefore, it was conducting electricity as I put it through there. So, it skewed my results horribly. So, experiment 4, yeah. Y'all are wondering, what was this one? And yes, there are things rats will not do. So, my 4th experiment, and my final one, what it talked about is whether there was a given length, a certain voltage could ignite. By ignite, I mean a little fire occurs and it breaks the strand. So, what's my question? Well, I just said it. What length can certain voltages ignite? Can 4.5 volts ignite 2 centimeters? Can it ignite 4? And so on and so forth. So what am I trying to prove, as y'all are wondering? My null hypothesis is that there was no maximum length a given amount of voltage could ignite. Reasonable, as you all hope. Okay, the way I set this up, I took a piece of wood, some nails, ruler, pencil. What I would do here, this is not very clear, I apologize. I would measure out a given length. This time, I took it out to 6 centimeters, measured it, hammered a couple nails into 0 and 6, tied a strand of coarse steel wool, because while fine steel wool will ignite really quickly, you cannot get a single strand easily. It's very difficult. While really coarse steel wool, pretty simple. So I got a piece out, I wrapped it around both nails, hooked a couple alligator clips to it, and then I would complete the circuit, usually catch it on fire. This is another picture of how the apparatus looked like. Really simple. I used a lot of 1.5 volt batteries, some 6 volts, a 9 volt. I had to really be up close to see if the wire was getting hot. Usually I'd put my fingers near it, feel if it was getting warm. Yeah, I would give it about 60 seconds. If it didn't ignite, I would say that there was no reaction, therefore that's as much as that voltage can handle. Here's a picture of what it would look like whenever I had a reaction actually. One time, well, once I hit 9 volts actually, it reacted immediately and sparks just flew out, almost got my shirt on fire. It was hilarious. Alright, so this is a table of all the data I collected. 0 stands for no ignition, X stands for ignition. And if you look at it, as it goes down here, every volt to go up, it gets about 1 or 2 more centimeters than the previous one. So I was wondering, alright, how would this look on a graph? So I took a graph and put a linear regression line to it. As you see, I mean, every piece of data I collected, really it was just spot on the graph, except for this one little piece there. It was kind of odd, but I made up for it by testing 5 centimeters, and it really shot up and covered everything. So, decided to get a function here and some values. My coefficient of determination, or my R squared, is 0.988. What that means is that 98, almost 99% of my data could be explained by that line. That's really amazing because that does not occur very often in a lab experiment. You often see that in nature. When you're replicating something though, not very often. My function, I ended up predicting that about 1.3 volts would ignite about every centimeter, which explained why my 1.5 volts would not ignite at 2 centimeters, but while 3 did ignite 2 centimeters. Variance here was 0.205. What variance means is that as I was collecting my data, it shows how accurate it is. If you have a high variance, the less accurate your data tends to be. Low variance, however, is usually really good. So, I ended up rejecting my null hypothesis because there was a maximum length that everything could ignite with the voltage. Now, I know you are wondering right now, alright, what's the point of this experiment? If you think about it, in laptops and computers, you have tons of wires. You also have a lot of voltage running through them. So, if you have wire that's too thin or there's just not enough length to it, the voltage will just ignite it and you got a fried computer. It's useless now. So what you have to do is keep a really thick wire in there or a longer strand to make up for it. Therefore, when the voltage hits it, it won't immediately ignite it. Yes?
Alright, I'm sorry.
No, I'm ready for questions.
Is that why, and this is unrelated to research, is that why when you do open your computer, like you see the wires that are kind of folded on top of each other, instead of just like directly to where it goes?
I believe that may be a reason. I'm no expert though.
Can I see your graph again? What's the dependent and independent variable in there?
Oh, I'm sorry. My independent variable was my length of wire, while my dependent, my voltage was my independent variable because I was able to control how much was running into the nails, while my strain of what it could ignite was my dependent variable.
And you got a point there by, how is that point there? How do I get a point at 2 for the
2 voltage would ignite approximately 1.3 volts or so. There's not a real specific. There's a very small.
That's the smallest?
That's the smallest.
Okay, that's the
2 volts would ignite, or 1.5 volts would ignite nothing, as you see in my graph. So 2 volts would ignite about, 1 or less than a centimeter.
So that's like at most, it'll ignite at most 1.3 centimeters?
1.3 centimeters, you get about 2.5 volts will ignite that. 2 volts will get about, 0.25.
Is that the actual intercepts that you obtained there? Like you actually hooked up 1.5 and nothing happened, then you hooked up
A 3 volt, and I got a reaction out. And
so you didn't hook up any type of find a way to give it 2 volts?
No, I didn't have any 1 volt batteries or 2 volt battery. Any other questions? Yes.
Okay, I think now I'm cleared up on what is there. So let me ask you to go to the next slide forward. You did a pretty good job in explaining. I want you now, we have an equation y equal mx plus b.
Correct.
In the context of this problem, tell us again what the m and the b are.
What the M is the amount of voltage it takes to ignite a minimum amount of strand of wire. What the B is the amount of, I believe, resistance it provides from the batteries. So while one strand will ignite at a given amount of voltage, if the voltage doesn't exceed a certain amount, this plays in where it's again negative or 0 value, therefore it will not ignite.
All right, so let's put it into calculus terms here. Since the slope is 1.3, let's call it, and the derivative of that function would be 1.3, what does that tell you happens every time you increase the voltage by 1?
Every time you increase the voltage by 1, what that tells me is while 1 would not actually get you a reaction, it would remain just sitting there for all eternity. While as you get up to 2 or more, you begin getting reactions.
Let me ask that again. The slope or the derivative is 1.3.
Right.
So what does that tell you about change? I'll give you a fill-in-the-blank question. For every increase of 1 volt, we could expect what?
We could expect a positive change, I believe, is what you're looking for.
For every, would somebody like to help him out?
1.3 change. Is that what you're trying to go
No,
for?
for every
Decrease
volt that you're
and
increasing or decreasing, you need 1.3 more centimeters of length to prevent it from
Every
catching fire.
volt you add is going to allow you to burn up about another 1.3 centimeters in length.
So if you want to prevent burning, you have to have more than 1.31 centimeters of length per volt.
And I just have one more thing. First of all, I think it's a great experiment. I mean, it has a real world application. You were able to explain it in terms of something that's sitting right in front of me. So for those of you who are thinking that if you've ever heard of Daggett's framework, this would be a category D lesson that you could do. Most of our lessons are A's. This would be a D lesson, which is good. It's an adaptation lesson. I want you to think again about your hypothesis. I'm really not in love with the way that you stated it. Because basically you talked about there's no maximum, whatever. Could you state it a little bit differently?
All right. Another way I could state it would be, all right, restating my null hypothesis would be that there's no length that a given amount of voltage cannot ignite. A given amount of voltage can ignite any length, so to speak.
Could you not just say there's no relationship between voltage and the amount that it will do? And then one of your byproducts is, oh, well, there is.
Yeah.
Maybe just not as worded. Okay. You know me, I'm a man of few words.
Right. Any other questions?
Good job.